Everything's really expensive.
It's gonna be all right. Let's print in color afterwards. But today, I'm gonna show you guys that.
Wait, good. What if we text? I love it.
Okay. So what's from like
That's because my corrections on the entire front sheet of the page. So
oh, it's
for which one? For this one? For the one that was supposed to be due today? Yeah, I just look at it like
I see. So I see.
top to bottom. I did have to go back and draw some pictures. All I had was
I know, I was
for this
thinking
one
just
because I didn't know like what the drawing of it was supposed to look like. So I had to look up a figure of like what they were supposed to look like. Yeah. No, I don't have any color in it, but I also don't really have anything in color. I may see to stop by after and just put a little bit of color for it. All I've got my notebook. And I have blue pens and black pens. That's all I have. So I know you're a color guy.
Stop by.
Yeah.
Save that. Save that.
Past summer, I was like, I'm not going to get I applied.
All right, so last week we had really good questions. We were trying to figure out the epinephrine signaling cascade, right? That how we're going to get the signal all the way from the extracellular part of the cell, all the way inside to get to the regulatory components down here, where we eventually hit cutting that glycogen into that glucose, right? So right now, all of you started working on this, making your own figures, right? This is the one that I put together in training today. It's going to be worth 4 points. I want you guys to think about drawing that figure as if we were drawing it for an exam, right? Where like last exam, I was asking, hey, can you compare these 2 pathways? But I want you to be thinking about how the molecule is going to look when they're on the, let's say, prime state versus when they're already activated. And now we have this really cool mechanism of once they get turned off. Right? So for that, I really want to bring up class participation. So I've had 2 students send me good questions. I think on Friday, I'm gonna double check the video, but I believe one of the students was like chasing down how does the signal go from one molecule to the next, right? That was a good question, so I'm gonna do that student bonus points. I had another student email me and talk about how there's 2 different pathways. So far, we've talked the one that goes, well, the drawing I talked to you guys about was basically this one, right? Where like, hey, we hit the receptor is gonna activate our primary signal, which is gonna be that the G protein, right? G protein keeps division cycles. We make that cyclic AMP, which will be our secondary messenger, and then we basically modify down this path, right? We're gonna activate protein kinase A, this thing's gonna go in, it's gonna phosphorylate the protein, this is gonna phosphorylate the next protein, and eventually this molecule is gonna give us the phosphate groups to help split the sugar chain into these individual molecules, right? This is one pathway, but there's a second one. We brought it up in lecture 18, which is when you're doing this type of regulation, the signal comes in and you basically almost activate multiple pathways to give you like this really broad or really specific response. In this case, what they're showing here is this is the other part. So now, again, there's our receptor, our G protein coupled receptor. This is that active subunit of that G protein, right? This is gonna act as the GEF, bring in that GTP. This is gonna go work with the molecules, and I work with this activated phospholipase C, right? So you guys remember this thing's now gonna be still sitting at the plasma membrane, and it's basically gonna signal of, you're gonna trim the fat portion that sits in your plasma membrane to the sugar molecule, right? 6 carbon chain. This is gonna get released, it'll go bind here, it binds to the receptor, and it releases the calcium. This calcium basically is going to come back into the picture. So this should be slide 18. So here we see that second signaling pathway, right? The signal's coming in, we're activating it. Phospholipase C, it's creating that sugar. We bring it to the ER, we release the calcium. That calcium actually goes and jumps in the middle of the current one that you guys have drawn, right? That signal is going to help us activate your phosphorylase kinase a little bit more active. Yeah. So now I want you guys should already have this one from last week, right? We talked about. Now I want you to incorporate this pathway into it. Yeah. So today, I've made my drawings trying to think about what's cool ways or what's the way that I can represent it or how I'll write it out myself in the midterm, hoping that I can give you the idea of how I want you guys to write it when you do the signaling pathway, right? So one of the ways you can do it is you put two drawings right next to each other and kind of power through them, right? So in the off state, this is our epinephrine receptor. You'd expect what's happening on the outside, right? Nothing should be bound to the extracellular. That's a big thing. The other one is down here. When you look at the activated state, we're going to find that the molecule does bind to the extracellular portion, but now we're going to switch jobs of what it does here. So what's the role of that receptor on the inside?
Change the shape.
Change the shape, right? And what does it do with that change of shape?
The G protein combined to the receptor.
You're correct, G protein, but what does it do to the G protein?
It allows it to bind to the receptor.
Correct. Now that they're bound, right? Receptor sitting with the G protein. How does the receptor affect the G protein? Starts with the G.
GTP. GTP.
It affects the GTP, but how does it do it? There's three-letter words that we know when you represent what happened. You guys remember GAP and GEF? So how is it behaving?
For the GEF, it acts as a guanine exchange factor, so it switches out the GDP or the GTP, causing the alpha subunit to detach.
Correct, right? So the molecule GDP that's turning there is going to get kicked out. You're going to have a brand new GTP come right in and replace it, right? So again, when you're writing this in the midterm, if you don't put the word GEF there, right, that's going to lose you some points. So make sure you guys bring it up.
What is GEF?
One more time, say it.
It's the guanine exchange factor. It switches the GDP attached to the GTP, which causes the alpha subunit to detach from the other two.
That's where some people, they instead of doing that drawing where a map takes it down, some people do drawings like this, where they use the arrows to help us tell the story, right? So in this case, we'll say, sorry, this is my rough chart. Let me zoom out. So when we're talking about signaling, I'm thinking about there's 3 steps. Normally we think that the signaling is prime, like it's ready to go, what's going to happen, but technically the signaling is off, right? Next step is what mechanism or what thing's going to help us do some kind of job to get us to the activated state. And then because signaling has to be controlled with communication, we have to have a way of ending that communication. This will be the next molecule, and this will be the modification. So here, beautifully, how Lindsay said it, right? There's your GD, there's your G protein, 2 subunits, there's that GTP. The goal is we're going to bring in a brand new GTP that's going to come in. We're going to kick out that GTP that's going to be gone. Right? And that's being done by the G protein couple receptor, aka the purple. Right? When it's doing that task, guanine nucleotide exchange factor. So it's behaving like a GEF. Right? So whenever you think about GEFs, they normally go in parallel with a cap. Like they're like the opposites, right? We've activated the system with the GEF. Now we have the 3 phosphates. Now this thing is powered up. That energy separates the alpha from the beta gamma. Now they can go do their own signaling. Eventually we want to get this thing to stop and we kill it off. That's why I need you guys to bring up this RGS, right? So this basically what it does is it's a GTPase activating protein. So what it's doing is it's behaving like a gap. It's that protein goes, binds to its alpha subunit, and it helps it so that it basically removes one of the phosphates and we catalyze that reaction. At which point we go back to this low energy state. This thing changes. Now it can go back to being this alpha beta gamma altogether. So we have the G protein, down to a GDP. So technically it's off, but also we kind of put it at almost at the starting place, right? So where again, it's off, where you can think of it as being primed, waiting for another round of signaling. Does that make sense? Pretty good? Yeah? All right. So when we're talking about that signaling, I want you to keep an eye on how these molecules are basically being modified as they're coming in and out from this inactive state to the active state, you know? So let's go back to this big picture. We did the, sorry, I forgot the receptor, guys. Let's go back. So this is my pretty picture. There's our receptor. Imagine right now, this is the plasma membrane that's sitting there, waiting for a signal to come in, right? No, what's going to happen is your ligand is going to bind, so your epinephrine will come in, binds to this part of your receptor. This is going to lead to it being active on the inside, right? Doing the next step. And now let's think about the different ways to shut it off, right? So one of the ways that we talked about last week was there's going to be kinases, so right? GPCR kinases, they're going to add these modifications, the 3 phosphorylations, which those end up being the mark for this protein called Receptor, which is here is drawn in brown. That's the one that's basically going to grab to the inside of the receptor, and now it's not going to be able to grab onto GTP anymore. Right? So technically, you pause the signal, turn off the signal, as long as this thing's kind of grabbing, holding on. Yeah. The other two that we talked about, I didn't have time to draw them, but it was, we can mess with the receptor itself, right? So one case is the receptor sitting on the plasma membrane, and you can just basically pull it inside into the cell into an endosome. When it's inside of an endosome, it's a little fat bubble inside of the extracellular matrix. So it means that it can't receive signal from the outside. So technically, you turn off the signal. You wait a little bit. If you wanted to, you can send it back to the plasma membrane, and you reset the signal, right? The other one, this is a permanent off, which is when you bring that receptor, you bring it into the cell itself, you send it to a lysosome. Lysosome is going to degrade that protein, you're basically going to destroy that protein, right? You're doing that, you're going to completely turn off the signal. You know, so this one has a little bit of multiple pathways. For the other one, I just need you guys to be comfortable with one. All right. Is this making sense? Pretty good? I know it's a complicated story. To me, the maps help me more. The diagrams is another way that you guys can look at it. So
where can we find access to that other pathway that you want us to add?
It's in lecture
Slide
18.
Thank you.
Slide 12. But I'll probably upload, or I'll paste this picture into one of the slides for today. Yeah. All right. So this is my rough drawing that I was prepping for this area. Let's go back, which was the activated G protein and the adenylyl cyclase, right? That's going to be the activating thing. Now that's going to behave different, right? Normally in an inactive state, what I expect to see is we're going to have a lot of ATP present. That's the high energy molecule. Everything's good. Your cell doesn't need it for sugar. When you start doing metabolic activity like running and stuff, you start burning your energy. You'll start bringing that ATP down. So that's going to be one of the really key signaling molecules. The way that this does it to make sure it's being activated is we're going to be turning that ATP into that cyclic format. Right? So a little P is connected to 2 parts of that sugar molecule. I mean, it might look a little different from the one you look, but it's just to help me remember. So in this case, when we have that inactive state, those pockets are empty. And basically here, this is our protein kinase A. When all 4 of them are together, it's off, right? These catalytic ones can't do their job, they're being repressed. Once cyclic AMP comes in, binds to the regulatory domain, takes that off. Now the catalytic part is free, right? So this is a protein kinase. So how does the protein kinase work?
Phosphorylation.
Phosphorylation. And in big key, where does it get its phosphate from?
GTP.
Not for this one.
Or ATP.
ATP. There we go. So in this case, right? Here we're thinking this is what protein kinase A is doing, right? This is your first kinase we're working on. In the off state, there's no cyclic AMP, everything's comes up, signaling is shut down. Once we bring in that cyclic AMP, we go to this phase, right? We go to the DC subunits. Now these are good kinases, they'll go phosphorylate things. I still need to figure out how we actually turn this off. think once the second AMP falls off, I'm not sure if they reclamp onto each other or degrade them. So this was still a question mark. But what we're looking at is now, how do these work as a kinase at the next level, right? So kinases go down, and then they hit this one, phosphorylase kinase, right? So for this one, we're taking that protein, this kinase itself is in the off state or prime state. Ready to go. Protein kinase comes in and it uses ATP. Brings in here, releases ATP, and gives us that phosphate group that's going to be attached to that protein. Again, now this is going to be an active kinase, right? Removing this phosphate by a phosphatase ends up bringing it again into the off state, but basically you reset it. So now it's in a prime state, ready for a new signaling molecule to hit to activate it, so it'll start working. This is the one, all right, the next two parts, it's the ones where I told you guys to try looking them up. So we have protein kinase A, phosphorylase kinase, and then we have the phosphorylase. What did you guys find out about the phosphorylase, how it works, or the protein kinase, phosphorylase kinase?
When I saw, they weren't fully sure how it worked, but to phosphorylate the glycogen phosphorylase, they think that they transfer phosphate from ATP to serine.
Correct, right? So you're saying from here to here, we're bringing in ATP, right? We're using that ATP to activate phosphorylase. So yeah, so that was a good point. That's correct, right? Because of that, because it's a kinase and we're using ATP to power up the reaction, that's what it's like. As long as this thing is phosphorylated, it has the ability to bring in ATP and give that phosphate to the next molecule. Yeah. All right, now here's the part where I got mixed up. On the next one, we chase down the glycogen phosphorylase. I'm gonna give 5 points for that first part. Those go to you. 5 points for the next person. It gives me that phosphorylase. There'll be bonuses on your midterm for participating.
Can you repeat the question?
How does this one, the glycogen phosphorylase, how does it work? It's not a kinase. It's a phosphorylase.
It adds a phosphate group to break up the bonds to glycogen.
Correct. Right. We add phosphate group. That's going to help us break it down. So where does the phosphate come from?
The phosphate groups that are added from the ATP.
From these guys?
Mm-hmm.
So that's what I was thinking last week. And that's why we're on the wrong page. So I'll give you 4 bonus points for helping out. For a correct answer, but answering, that's going to be the bonus 4. Yeah. So we got it wrong. High five. We're on the same team. You know, that's what I thought. Well, did anybody figure out how it works differently?
Serine residues?
Sorry, so like where does the phosphate itself, where did it come from? Like when I was doing my drawing over here, you guys see I draw like here. We have ATP, it has a phosphate, we break it up, and we this is the kinase in the inactive state. We're going to activate it with protein kinase A, but we're stealing the phosphate group from an ATP to put it here. Right? In that other reaction, where's the phosphate coming from?
Glucose?
Not glucose. Want me to look it up? I know you have it already.
I know, I'm just, yeah.
All right.
No, I don't want to miss.
Wednesday. That's my big question to you guys. Where's that phosphate coming from? Whoever figures it out, it's 5 points, extra credit for one of your midterms. Write your name down. And then write your name down on this one. Is the question making sense to you guys? Yeah. So everything else we call them hint hint. Everything else we call it a kinase. This thing's a phosphorylase. I thought it was a phospholylase in my head, and that's what tricked me all up, thinking like you can pathway they can transfer the phosphate. It's not that one, right? There's a different way where we're getting that phosphate. Everyone's gonna try it out. It's 5 points, you guys. That's a lot for a midterm, yeah? All right, so We're gonna leave it till Wednesday. But for this one, I was looking at some of you guys' figures that you guys have been turning in already. Keep them so you can add that second pathway. The other thing I want you guys to do is, and some of them I saw they were just drawings. You need to give me some written portion where you give me your logic of how we're finding the molecules, right? Either you can do it like this, you can draw out, hey, in a repressed state, I expect to have, that up there with no get function, a bunch of ATP, kinase A, protein kinase A should be clumped together. This is not phosphorylated, that's not phosphorylated, and my glycogen again, it's all stuck together. In the active state, I should be looking at all the big differences, right? Which is that receptor, we're going to be sitting with epinephrine. G protein is going to have the alpha unit sitting with GTP now, right? Adenine cyclase should be active, aka we're making that ATP, and we're switching it to make a bunch of this cyclic AMP, right? Protein kinase A, cyclic AMP is basically binding with the regulatory domain, and that catalytic portion is now able to do its job. That gives us that first phosphate. Here I would almost draw in ATP goes in, ADP goes out. That's our first transfer. Phosphorylase kinase, which as for the kinase to the phosphorylase, same thing. ATP comes in, we steal the phosphate group, ADP moves out. There are basically the phosphates. From here to here, it's the one that you guys need to figure it out. Whoever gets me the answer, that's 5-point bonus for your midterm. Yeah. So tighten up your notes. The other one, like I said, you can do them like this on the right. You can also do them like this on the left. You can do the drawings and just show how at each phase you have the different changes, the different confirmations. Feeling good? Yeah? All right.
How does CAMP turn back into ATP?
I think.
Isn't it AMP, just AM?
Yeah, so it goes from. Give me a second, sorry. Basically this thing, cyclic AMP, phosphodiesterase. It's gonna basically cleave this bottom covalent bond, and it'll release it, and so now it's just a regular AMP. And that ends up kind of like telling the signal to be off. I think these, they have to go get recharged, and it's going to be a thing that's going to add the phosphates back to it. But I think that's, we have to get into like the ER and stuff. But I'm okay with you guys just going from that left to right on this case. Yeah. Any other question on this guy?
So how much did you want us to add about the off state? You were saying with like the receptor, the G protein receptor. We need to like.
There, yeah. 3 different options. I need you to be comfortable with all 3.
And like in our depiction, you want us to draw each one? Or
just depiction? Just give me a sign, draw one, and give me a sign note that 2 others exist. Okay. It depends on what you want to do. If you want that receptor to kill the signal and have communication shut down, you want that thing to get endocytosis and then be great with protein. If you're just trying to quiet the signal down for a little bit, right, you can bring it into an endosome, hold on to it for a little bit so you won't let it against it, and then you can let it go. Or the other one is you can argue with this one. When you have that complex of a kinase comes in, these GPCR kinases, they'll do that first level of phosphorylation, then the arrestin comes in and it holds on to it for a while. Right? Holding on to it, aka blocks away the G protein. So if no signaling is coming in, nothing's going to keep moving forward. What's eventually going to happen is you have this arrestin kind of fall off. These phosphorylations will get kicked off by a phosphatase, get rid of phosphates, and then you have a good receptor. Yeah. All right, any more questions on this one? All right, so I'm gonna put in a thing on white space that it's due on Wednesday, or Wednesday before class. Give me the full drawing if you want to upload the pictures there. Also take them in person. So, yeah. Pretty good? So yeah, I'm thinking of doing the thing of keeping you guys bonuses. So when I ask you guys questions in class or challenges, those will be like extra points assignments. I'll just add them to your grade in your terms. So yeah, so from now on, if I give you guys challenge homeworks or stuff to take them out, You guys bring back whatever answer you are. If you're correct, you get the full bonus. If you're incorrect or you're trying, you get automatically still 80%. The lowest participation, I don't care if you're right or wrong. I just need you to try looking for stuff up and participate. Everyone cool with that? Yeah? All right, let's do it. Ooh, that was a quick one. Yeah, sorry, I talked for a while, you guys. All right, let's get a little bit into today's lecture. So now we're looking at a new type of receptor and the tyrosine kinases, right? So what we're looking at, we're going to be looking at how they're phosphorylating different amino acids. So on top, we have our serine, right? There's your alpha carbon right there, your N terminus, your C terminus, and then this is your R, right? What we're going to be looking for is going to be an OH group. So basically our receptor of where when we add that phosphate group, we're basically going to attach it to that linkage. So that's why serine is one of the ones that can accept it. Also, 309 is another amino acid that can accept them. Basically what we're doing is, again, we're grabbing our phosphate, going from that ATP, we're stealing one of those phosphate groups, leaving it as an ADP, and now that phosphate sticking to that specific amino acid. Tyrosine is just a little bit different, and it's just because the shape's a little bit different. Instead of having just a linear carbon chain, now we have a carbon ring. The thing is, at the end, we got that hydroxyl, and that's the place where we can glue in those make that phosphate chain. So again, tyrosine kinase, we steal that phosphate group from ATP, we leave it as ADP, dump it out, and there's that phosphate. The way that we turn both of these off is going to be our phosphatases. So again, this will be a different protein. It can recognize that amino acid, and what it's going to do is going to strip away that phosphate group using water. Right? So it's going to grab that phosphate, cut it off, and you're releasing what's called an inorganic phosphate. So whenever you guys see this P with a little I, that's what we're talking about. You've dumped it out, and you basically return that amino acid to the initial state. So this is the kind of thing that we're talking about, those different kinases, how they were working. They're able to get activated, so they're primed, ready to go. They'll get activated by the kinase themselves. Now this will be able to do their job. Phosphatases come in, take away that phosphate group, and it pops them back into this inactive state. Yeah, so keep in mind these two opposing functions, kinases and phosphatases. All right, so when we're activating these kind of receptors, what we're going to be looking at, here you're looking at, this is your extracellular portion, right? So we're outside the cell. This is your inactive state. Here, your growth factor would be your ligand, right? That molecule coming in is going to get your receptor kind of clump onto itself. It's going to change its shape. It's going to change its function at that point. In which case, what you'll see is that these have kinase-like functions. So it means that they want to do the thing of finding someone else and giving the phosphate group to them. Right? What ends up happening is that both of them will actually like cross-reacting. This kinase domain will phosphorylate the other receptor. This kinase domain will phosphorylate the other receptor. So they're like cross-acting. So they kind of have to come in as a pair of groups to kind of work with each other. Does that make sense? Now we have this phosphorylation on the inside. We've transferred that information, okay, the signal's on because we have a ligand binding to now this new phosphate state. Now this is where we're going to start setting up the same thing. Yes.
What's the N and the C terminus again?
When you're talking, anybody want to help me with this one? N and C. What are we talking about?
It's inside and outside.
I think N is like the head of the protein or the polypeptide chain, and C is the end of the polypeptide chain.
Correct. All right, so remember how when we were talking about a protein, like this guy, any amino acid, you have this, your amine group. So the NH3 or NH2, that's like the front half. Like that's when I'm talking about DNA and I go 5', that's 5'. And then here's your C double bonded O, CO. That's basically your 3' of a protein. So this is a single long
the amine group at the top.
Yeah. So it's one long single amino acid chain. The N terminus would be like, let's say that's where we probably find near the 5' side of the RNA. And then this will be basically the end where we find the stop codon, right? There is no correlation between the N and outside the cell or C and inside the cell. That's a really good question.
Okay.
They have signals that when they're trying to pump the, like you have to like have the ribosome push the protein into the plasma membrane. Depending on what signal comes first, some signals tell it when you want to put this chain in, to put it in like this, where the N terminus is going to be facing up. There's different sequences that tell it to make sure that the N terminus is facing in. So different proteins, you can set them up with like one portion of it sticking in the N terminus on the inside. You can control the whole tail, and at the end you can leave it to the tail also on the inside. Or you can set them up where, you know, any combination, both outside, inside and out, outside and in, whatever you want. You know, so no correlation at all, but good question. All right, back to this guy. Signalings come in. Right, the next thing, next big thing is that phosphorylation mark is going to be that thing that's going to help us almost sort of like a docking site. This thing is, hey, this domain is active. We'll start bringing complexes together. This is where you have that downstream signaling molecule kind of coming in, but it's based on having that phosphorylation. No phosphorylation, this is not going to work. So when it's bringing some of these molecules in, some of the things that they'll do is you will be signaling, again, that same cascades. Kinase hits another kinase, the kinase hits another kinase, and that's how we transfer the signal down till we get to that final molecule. Here, this is what they're doing. They're bringing in the kinases, right? Having those kinase presence are going to be giving you that job, which is like they can go, they can help, like kind of like push that interaction of like, hey, let's phosphorylate your opposing chain, right? They also, because they're kinases, they're basically stuck on that site, and their job is they just want to throw phosphate groups on it. Because they're stuck there, they have more and more chances of giving you more phosphorylations on your same tail. Right? So the longer they stay there, the more phosphorylation marks you'll have, aka you'll make a stronger, like stronger and stronger signal that this thing is ready to go. All right, so for this, it's a big family, there's a lot of them. So we have the receptors on the outside. That's going to tell us what they're going to interact with on the inside. But the goal is we're going to get the signal to feed into the G proteins. The G proteins themselves, there's it's like a big family, right? They have slightly structural difference, aka gives us different binding partners, aka we can target different pathways. So for this one, I would not memorize the names of all these guys. The ones people talk a lot about is Rho and RAS. Just remember those two families. Yeah.
Sorry, this is a question about the slide before. So in the last photo, is it both cross-phosphorylating and phosphorylating its own?
And this one. So this one is just, they're like phosphorylating each other. I don't think they can phosphorylate themselves.
But on the one with the kinases.
Yeah, because now you have a lot more flexibility.
So it's doing both?
Yeah.
Okay.
So you can either go across or you can kind of go into your own chain. Because the amino acids, like, they're linked up, but they have like limits to how much you can bend them or how much flexibility that they have. Once you bring in another bigger complex or bigger protein, it gives you a little bit more room to kind of jiggle around itself. All right. So GTPs, and now here, same thing. This is going to be my favorite stuff about how we're going to get the signal down and how they're going to be behaving different, right? In this case, the big thing to focus on here is we're looking at that get function, right? So what's the get function again?
The guanine exchange factor.
Right, guanine exchange factor, right? So here, we want you guys to be showing that off, right? RAS is currently sitting with a GDP, right? That get function is going to kick out that old GDP and we're going to bring a brand new high energy GTP molecule. Boom, now we have that active state, right? So RAS has GTP. This gives us the next pathway of now we're interacting with RAF itself, right? And again, these kinases, we're transferring the signal down, and every time I want you guys to keep an eye on what we're doing, right? First one is GTP, we're swapping in that molecule. The next one, we're popping over, and now we're using ATPs, right? And the goal here is every time we have one of these kinases give us or activate the next molecule in their chain, we're stealing that phosphate group from ATP and we're leaving it as an ADP. That phosphate group is now on our new kinase. This can do this next pathway, right? It's going to use ATP. We're going to steal one of its phosphates, activate the ERK. And so this is how we can get kinases to basically signal down one to the next. Right? And we're using ATP to power this whole reaction. And this is pretty cool. There's like proteins that behave like scaffolds. So what they do is, in some cases, it's like you activate the first kinase. You would technically have to wait till that finds the next molecule to lead to the phosphorylation of that one. But having a scaffold, you have this really cool benefit that basically these little coupling sites end up putting the kinases in the right order, right? So we're gonna go RAF, MEC, ERK, right? They're in right order. One phosphorylates, the next one's already in the same neighborhood, ready to go. You phosphorylate the next one, this one's ready to go, phosphorylates the next one, and now we produce a response molecule. Yeah, so these kind of help speed up the reaction. All right, cool thing about these, but things that makes them a little bit complicated to work with. And I think in the beginning, when they were used to work with these, they used to get into fights about this, trying to figure out like, oh, my receptor activates it, and the other group would be like, no, my receptor does it. And it's because they can, as they activate pathways, right? Like this is the one we talked about last week, your G protein coupled receptor. You can see we can do the G protein that cyclates and has like its own little pathway. Remember, the G protein also hits that phospholipase C, right? This is that thing I was talking about, the sugars and the fats. These end up producing calcium, vanadium. You already have that signaling being activated. This receptor tyrosine kinase can do the same thing. It can activate that phospholipase C and basically can induce the same pathway as the other. So once they do that, again, we have that small ligand bind on the outside. We can activate multiple chains or multiple pathways. These will actually activate and hit multiple targets, right? Here you can see we hit these three. Other receptors, same thing. Because the signal gets in, it amplifies, and it can like diversify, hit multiple pathways. It gives us a lot of control. We can control different targets. The only thing that makes it hard to work with is that sometimes you'll have crosstalk. One signaling pathway actually can do the same thing as a different one. No. All right, so part of this regulation, I'm gonna bring it up a little bit more next week, is that we're gonna be talking about how some of these pathways, they have ways that, like positive feedback loops, which is they'll try to self-amplify. So it's like once we receive the signal, it comes in, we want to make sure that that response is very strong. So we have to have ways of the cells to tell themselves, we received a small amount, but we need to keep going and make more of this, right? We're also gonna have negative ones where it'll be the signaling is coming in, and some aspect of itself will make a molecule that will go back and inhibit something from upstream or like something intermediate, and it's a way to kind of kill off the signal. So here, let's look at a negative feedback loop. And then what's gonna happen here is your signal's coming in, right? Here from left to right, we're going from, this is gonna be that next signaling molecule. We have a kinase function, aka ATPs coming in. We steal a phosphate group, now it's in the active state. This will go and it'll activate some molecule, right? That molecule will be that negative feedback, which will be this inhibitory, it's a phosphatase. By doing so, it'll go back to the same molecule that it just came from. It'll end up removing this phosphate group, right? And now it puts it back into the like prime state, aka it's not active anymore, right? So within its own pathway, it'll try to shut itself off. The cool one that I like is the GPCR receptor. The one that thing gets activated when the signaling comes in. It goes back, phosphorylates the receptor, and that's what helps bring in the arrestin. So it'll be like a negative feedback loop. The opposite to that is going to be these positive ones, right? In which case, you're looking at things that will try to make the signal stronger. So for this, again, we've turned the signal. There's our first kinase. This is going to, again, use that ATP. We're going to phosphorylate this B molecule. Now this becomes an active kinase, and sometimes it'll kinase function on itself. So if you started making 4 of these molecules, when you have 4 molecules present, what's going to happen is, if the signal is still present, you'll have phosphorylation coming from this side and phosphorylation coming from this side, making it stronger. The only issue with this is that once this is very active, we don't even care about the left side anymore, right? Because it'll be like, we can have like our own self-sustained phosphorylation cycle. With the same kinase will keep phosphorylating itself, and it just have a really strong robust signal, despite the extracellular stuff. Yeah. All right. So we're going to go a little bit into details. I'll kind of show some of the pathways. And then some of them I'll show you how we're going to start drawing our arrows a little bit different. So when we explain some things, a positive feedback loop versus a negative one. Yeah. All right. Any questions for today? No? All right. I probably won't do cards today, so I'll give you guys points from the paper you guys are writing, or that guideline you guys are creating. Yeah. I might give you, I'm going to move it up. Last time I said 4, but I think I'll give you guys more points because you guys are going to add the sugar fat. Also, like to see. Yeah. All right, cool. Any questions? All right, so you guys on Wednesday.